Hello friends, welcome after break. Today we shall be discussing in the video performance levels of structures and the acceptance criteria corresponding to the performance levels. So the basic question is, why do we go for performance based seismic design when already there are so many design codes available in every country? The answer is the codal design procedures are only prescriptive in nature. You have to obey these prescriptions so that you are legally sound in designing. But you remain in wilderness what your structure will perform during an earthquake. You don't have any answer to this. You don't have any control over the performance of the structures in terms of say drift, in terms of damage. You cannot yourself decide that I will allow this much amount of damage in the structure and no more. And you cannot decide also the level of seismicity under which you design. For example, in Indian condition, your maximum shaking level corresponding to the design code is only 0.36 G. You cannot go beyond that. But if you want a structure, maybe a nuclear structure of higher level than this seismicity, then what do you do? So in the codal method, it is all prescriptive and you are bound by those prescriptions. You don't have any choice from yourself and you remain in dark about the final outcome of the structure that you have designed. To overcome all this, we go for performance-based seismic design where we have much more control on the design parameters and also choice about the objectives and the hazard levels. So after this we will go to the video. So title of the video is Performance Levels and Acceptance Criteria. So this you can assume to be a starter point for our performance based seismic design within the periphery of this channel. This is the entry video. So performance based seismic design involves two things. One is designing for some predefined target design objectives and that too under some specified hazard level. So these target objectives you have to select in the beginning. This as a designer you may select, or the client may come and he says that he wants this kind of outcome from his structure and thereby you can decide the target objectives for the structure. And then also you have to decide the hazard level. Do you want under design basis earthquake, which is regular earthquake, frequent earthquake, or you want under infrequent earthquake, which takes place at large time interval, large period of return. In other words, the level of the seismicity you can decide. Now what are the predefined target objectives? The predefined target objectives may include interstory drift ratio. In the next slide, we shall discuss about the interstory drift ratio. It can also tell you about the quantum of damage as an objective in the design. Quantum of damage means how much plastic deformation has taken place in the elements of the structure. It may include crack width and other parameters. There can be more parameters in the design objectives, but of late, as far as my knowledge goes, only interstory drift ratio and quantum of damage in terms of plastic rotations have been accommodated as design objectives in the PBSD. In future, certainly more objectives will come, like crack width maybe we shall be able to accommodate in future. Hazard level indicates the design spectrum of the code. Every country has their code and the level of seismicity of that very design spectrum you can set by taking a fraction of G. For example, you take Euro code and you set your fraction of G as 0.45 G, then this is one kind of seismic level. If you select 0.65 G, then it is a higher seismic level for that very code. So we have the predefined target design objectives which we have to select depending on the nature of the structure, depending on the outcome of the structure we want, and depending on the economy you want to have for the structure. And the hazard level is shown here. It is given in every code, corresponding hazard levels. So with these two, after selecting these two, you design the structure. There will be engineering process for design that we shall take up gradually in future videos, and you get the structure after designing. Now whether the structure you have designed for your predefined target objectives under the specified hazard level are able to sustain, able to show those objectives under the specified hazard level, that you have to ensure now. That can be done via the nonlinear analysis of this design structure. So this structure that you have designed is now to be evaluated. So evaluation is done through nonlinear analysis, pushover analysis and time history analysis, and the results of this will show you whether the target objectives set in the beginning are satisfied or not. While evaluating through in the nonlinear procedure, you are setting the hazard level corresponding to the specified hazard level you have taken in the beginning. So if it is satisfactory, then you may stop. If it is not satisfactory, you have to redesign it with some modifications and again get the structure and evaluate it again and see whether it is satisfactory. So this is the outline of the design in the PBSD. Now we want to study what is interstory drift ratio. Before that, we take up this video which is moving in the first mode. This building is moving in the first mode. So while it is moving, one story is moving further away from the next story. That is what is the movement is. One bay of the frame here in this figure. Say we take one story where the interstory height is hs. And one floor is say ith floor, the next floor is I plus 1th floor. So ith floor is getting a displacement of delta I with respect to the ground, and I plus 1th floor is getting a displacement from this point to this point, which is delta I plus 1 with respect to the ground. So these two are written here. Now if I subtract this delta I plus 1, delta I from delta I plus 1, then that parameter is called the story drift. That is, this much drift has taken place between these two stories. You may know that the discomfort that one will feel is not with respect to the ground displacement delta I plus 1, but with respect to the relative displacement between the floor above and floor below, that is the story drift delta I plus 1 minus delta I. Now if I divide this value of the story drift by the height of story hs, then the result is called the interstory drift ratio IDR. So this is what is your, now this IDR can be expressed in other ways also. So if the height is hs and if the angle subtended here is theta for the drift, story drift delta I plus 1 minus delta I, then the division of this delta I plus 1 minus delta I divided by hs is the IDR, is nothing but tangent of the angle here in between, and because these angles are small, I can say this is equal to theta also. So IDR can be expressed in terms of angle in radian, and this can be expressed also in percentage. So suppose we to consider a 2% drift, it indicates 0.02 radian angle is the drift we are allowing between the two adjacent floors. So you can also write as a ratio, because this IDR is a ratio. So this IDR you can also write as a ratio of 0.02. So that is what is interstory drift ratio IDR. So there will be IDR values between each adjacent floors. If there are 10-story building, then there will be 10 values of the IDR, and these values will be changing at every instant of time in the dynamic analysis of the structure. So later you can plot this, and out of this, whatever the maximum drift you get, that is the drift of the building, maximum IDR of the building. So why we study the IDR? What is the importance of the IDR? IDR is important because, as I said, the discomfort that you feel is based on the IDR between the drift between the adjacent floors and the height. Furthermore, if you have mounted some equipment, say in a hospital or some laboratory, some equipment vertically mounted in the wall, then the top of the equipment will be moving in a different magnitude than the bottom of the equipment. As such, the effect of drift will be coming on the equipment and the equipment may get damaged. Similarly, you can have a horizontally mounted equipment in the wall or in the floor, and due to the sway, due to the twist, etc., the differential movement will take place between the two ends of the equipment, and as a result it may get damaged. However, when we are taking effect of drift, it is the question of vertical here, because horizontal drift we have not considered so far. Horizontal drift will take place mainly due to torsional effect, the twisting of the rigid diaphragm of the building. Now we take up the performance levels of structures. So performance levels mean a damage state of the structural element or a structure. Damage state can be quantified in the amount of by the amount of plastic deformation. The plastic deformation can be of several types as shown here. Plastic displacement delta P, plastic rotation theta P, plastic curvature phi P, plastic strain epsilon P, plastic twisting phi P, and plastic shearing also delta SP. So each of these damage is a kind of limit state. We have seen the limit state design in steel structures and concrete structures. So there the limit states are qualitative in nature or of particular types only. Limit state of collapse, limit state of serviceability, etc., particular types. But here the limit states are with respect to some deformation, and the amount of deformation also will be mattering here. The amount of plastic deformation will be designating the structural performance levels, either high level performance, medium level performance, or low level performance. We have taken up a curve here. This curve is the force deformation response of a structure or a structural element. So in the beginning the response is elastic. It remains elastic up to the end of the elastic limit, and the deformation, maximum deformation here is maximum elastic deformation is also equal to the yield deformation, after which it yields. So this delta y is yield deformation where yield starts. On the other way, it can also be said as the maximum elastic deformation. Now if I take any point on this response curve A, we have the total deformation from this origin up to here, and this deformation consists of the elastic deformation and the plastic deformation. That is what we have written here. The delta A, total deformation up to the point A, is equal to elastic delta y plus plastic delta P A. Similarly with the point B, delta B equal to delta y plus delta PB. Delta PB is from here to here, plastic. So the amount of plasticity, obviously clear from the figure, amount of plasticity is more at the point B than at the point A, or the point B has suffered more damage than the point A. Performance levels will mean a damage state of a structural element or structure, and damage a limit state as we have discussed. So based on the amount of damage it is undergoing, we will give some nomenclature, and those will be the performance levels for the structure and structural elements. The elastic deformation is regainable, that is, once the load is removed it will go back to the original position, and so this part is negligible, means not to be considered in the nomenclature of the performance levels. So only the plastic part of the deformation will be designating the performance levels. So high performance levels will indicate low plastic range. Low performance level will indicate we are accommodating more damage or more plasticity in the state. Now we study the performance levels. Performance level cut. Now we take up the performance levels. Performance level means a damage state of a structural element or a structure. Damage state can be quantified by the amount of plastic deformation. So it undergoes plastic deformation, and that plastic deformation amount will tell about the damage state of the element or the structure. So plastic deformation includes plastic displacement delta p, plastic rotation theta p, plastic curvature phi p, plastic strain epsilon p, plastic twisting capital phi p, plastic shearing delta sp, etc. So in terms of these plastic deformations, we will be able to quantify the damage state. Damage state is also a limit state, but in a slightly different context. We have studied the limit state in concrete and steel. There it was a collapse prevention limit state, serviceability limit state, etc. 3 types. But here limit states are within a particular type, say displacement, plastic displacement we consider. Then the limit states can be at different displacement, different limit states. So within a particular category of deformation, you can have several limit states in this concept. We have taken a forced deformation behavior for a structural element or a structure. Initially the response is elastic, straight line. At the end it yields here, and displacement up to this yield point is the elastic displacement called delta y. For our future videos also, remember delta y is the yield displacement as well as it is the elastic displacement maximum that is possible at the end of the elastic limit. Now we consider a point A on the forced deformation curve. It has a total deformation starting from the origin up to this point, out of which this delta y is the elastic and delta PA is the plastic part. Similarly, another point we have taken further away on the deformation, forced deformation behavior. So here the elastic is delta y, plastic is delta PB. So the total deformation we shall write down like this: delta A equal to delta y plus delta PA, and delta B equal to delta y plus delta PB. Performance levels means a damage state of a structural element or a structure, and as we have said, the damage stage will be quantified by the plastic deformation. In this figure, we have taken moment versus rotation. So moment rotation response, say for a beam element, the nature is more or less similar. In the beginning it is elastic, so it is theta y, the yield rotation. Then for the point A it is theta PA, for point B it is theta PB. As in the previous slide, here also the point B has suffered more damage than the point A, because the plastic deformation amount theta PB here is more than theta PA. So here also we can write like this: theta A equal to theta y plus theta PA, and theta B equal to theta y plus theta PB. Now this total angular deformation at the point is your design drift value, because we have seen the drift can be expressed in terms of angle. So this total deformation at the point A is the design drift for the point A, and the total deformation at the point B is the design drift at the point B. That is, if you want a structure to be designed for say deformation up to point B, then you have to design it for this drift theta D equal to theta B. We have considered again a response curve. This is called the pushover curve. It is between the roof displacement and the base shear in the building, or even other structure also, same principle hold good. Their roof will mean the top of the structure. So when it is beyond the elastic point, damage has taken place, and we take a point here very near to the elastic point, the damage is less. This damage state we call as IO, immediate occupancy. What does it mean? It means In a post-earthquake scenario, you can immediately occupy the building without major repair. That's why it is called immediate occupancy performance level. Further away on the pushover curve, where damage is still more, we call it as the life safety point. So performance level is life safety, the damage is medium damage, and further away you have very large scale damage, which is severe damage. It is called the collapse prevention. So life safety means the life is not threatened. The damage is there, but the damage is not so high that life will be threatened inside the building. Life may be threatened due to falling hazard, due to the collapse of the structural element, so that the structural or a part of the structure becomes unstable. So in life safety, life is not threatened. In collapse prevention, the structure is almost fully damaged. However, it is retaining the capacity to retain the gravity loads, and so it does not collapse. That's why it is called collapse prevention CP. So we have measured 3 damage states or performance levels: immediate occupancy, life safety, and collapse prevention. Obviously, a immediate occupancy building will be performing much better during earthquake. Damage will be almost negligible. Life safety will be suffering damage but not threatening the life. Collapse prevention will be suffering very large scale damage in structural as well as non-structural components, but it is not falling down, it is not collapsing. So we are putting IO for immediate occupancy, LS for life safety, and CP for collapse prevention performance levels. So these are all damage states or performance levels as we have discussed. We have taken this pushover curve once again. So what was missing in the previous slide is the in between the IO and LS, this damage state, what name you will give. So this is called damage control range, because it is not a particular point like IO, LS or CP. IO, LS, CP are discrete points on the force deformation curve. Here it is a range from IO to LS. This is called damage control range, and the range between LS and CP is called limited safety range. So you can build your structure for IO level, LS level or CP level. You can also build your structure for lying in the damage control range or lying in the limited safety range. So we have the IO immediate occupancy, LS life safety, and CP collapse prevention. In between we have the damage control range between IO and LS, and between LS and CP we have the limited safety range. These ranges are also performance ranges, performance level ranges. Thank you very much for coming up to this. It has taken a little time. Please subscribe the channel, like the videos and comments. If you have any query, you can put in the comment box. I shall be glad to answer this. Thank you very much.